This week's topic is logistic regression. And there's a big change this week. In logistic regression, the y variable is categorical. And this is a key thing we'll need to know throughout this lecture. So make sure to write down the key note that in linear regression, the y variable is quantitative. But in this week, with logistic regression, we will be doing a categorical y. So let's talk about the overview of what is logistic regression. Well, in logistic regression, we are predicting this two-level categorical y. This is just the regular logistic regression. There are higher levels of logistic regression called multinomial logistic regression. That is when you will have a y with more than two levels. But for this class and for right now, we will focus on a y variable that has two levels. That means it could be answered yes, no, true, false, stay, churn. Churn is when someone leaves their cell phone contract or doesn't renew it. So they churn, or they either stay with the cell phone contract. We have someone pay on time, or they could default. Now the key thing here is, since it's a categorical variable, we'll focus on predicting the probability of the level of interest. So in logistic regression, we want to predict a two-level categorical variable, and we are interested in predicting the level of interest. We have to think, what is probability though? Now, probability is a long-run frequency of the percent of time we see something occur. It's not one time when you look at something and if it occurs or doesn't occur. It's over multiple trials, and we call this the law of large numbers. And you can see right here, if you're rolling a dice right here and you're trying to get a 7 or get a random number generator to generate 7, well, every once in a while it will generate 7 right here. We're just highlighting the cases where 7 appears. It appears on trial 3, 6, and 7. And then you will start to see the true probability of obtaining a 7 after doing repeated trials in the long run. And this is what probability is. So notice at the start we didn't get 7s, and then we had a spike of 7s, but in the long run frequency, we start to go to the true probability, which the true probability is around 10%. And of course, we can think mathematically, if there's 10 numbers and we're choosing 1 out of 10, the probability will be 10% of getting 7 when you generate a number 0 through 9 or 1 through 10. With that in mind, remember, probability is the long-run frequency of the observed event occurring. Here we are with another one where we are looking at someone either making a purchase or not making a purchase. And we would see this if we watch customers repeatedly, that the fraction of customers making a purchase would approach 70% if that's the truth as we increase the long number of purchases. This is a log scale right here, so we are in the hundreds of thousands, or millions actually, because this would be 1 million trials, 6 zeros afterwards going off the screen right there. But we would be at 1 million trials at this point, so a very high number of trials. And this is just how we think about the probability theoretically to understand that the probability of something occurring is the long-run frequency of the percent of time it occurs. And we can see this with the law of large numbers. So, well, more in depth, what is probability? Probability is contained between the interval 0 and 1, with 0 meaning it can never, ever occur. I like to say this is the probability of me meeting Deadpool, so that can't occur. I'm never going to meet Deadpool, sad day. Where 1 is going to be the probability of things that must occur, like doing great on the test. That's the probability of 1, right? That means it must occur. So 0 and 1 are the upper and lower ends, respectively, of probability. We can think about things like the complement. So in the previous example, we had the probability of someone making a purchase of 70%. So the probability of not making a purchase right here would be just 1 minus the probability of the event. P of A just means probability of event or thing that we are interested in. So 1 minus the probability of purchasing would be not purchasing, and that's kind of the key word right here when you find it. And of course, if you do 1 minus not A, you'll get A. So you can just go back and forth between the event itself and the complement when we look at things occurring, whether or not someone purchases or not purchases or purchases. It just depends on what we want to predict. Because maybe the model has been created such that we predict the probability of getting a 7, but maybe we want the probability out of the model of not getting a 7. As far as we can see right here, the probability of not getting a 7 would be 90%. Because the probability of getting a 7 is estimated to be 10%. We can easily do the complement right there, and we would know that something and its complement add up to 1, because that's everything that can occur. So do not confuse these values, this 10%, 7%, 70%, 30% with p-values. The p-value is the probability of our results or results from our stream having by random chance variation given that the null is true. There is no null hypothesis here. The p in p-value does stand for probability, so p-values are probabilities, but they're not the same thing as us talking about the probability of the logistic regression y variable of interest. So when we do these probabilities right here, we are finding the probability of something occurring that we are interested in rather than finding out the statistical significance of a model. Once again, here we're looking at the probability of someone making a purchase, and over here this is not statistically significant, as in that doesn't apply to it. So if I asked you, is that statistically significant, you would say, does not apply. That is not a question we would ask with that. Because right there, that is not a p-value. That is just the probability of something occurring unrelated to statistical significance. So make sure to not blend these topics together. They are both probabilities, but the output of a y variable in this model will be a probability, but not a p-value, because it doesn't relate to statistical significance. So how are we going to do these models? What is simple logistic regression? Well, simple means 1x, and regression means taking a y and going on the x, and we're only going to have 1x, and logistic speaks to the shape of the curve, which is the sigmoidal curve. Sigmoidal, hopefully don't make a typo on this, sigmoidal means S-shaped, sigmoidal. We'll do a quick check over here on the other screen just to make sure we spelled it correctly. Don't have the autocomplete on that. And we got it right, sigmoidal. Usually helps to have autocomplete. But with sigmoidal right here, focus on the first part of it, the sigmoidal, and that's the S shape of the logistic curve, which is going to be very important when we talk about how it works. So this is where you need to pause and take a note. In logistic regression, the level of interest is last. So in logistic regression, in logistic regression, the level of interest is last. Some alliteration right there to help remember, because previously with reference levels, we had the reference level is first with categorical x's, such as if we have days of the week. Friday is the reference day of the week, but that deals with x's that are categorical. So categorical x's have reference levels. Logistic has a level of interest. You can also kind of talk about the reference level there. I don't prefer to. I prefer to only talk about the level of interest, the thing we are interested in. You can recode things in logistic, but by default, JUMP will use the last level. So if you go way back to variables like no and yes, already put in alphabetical order for you. When we predict the probability of something here, will we predict the probability of no, or will we predict the probability of yes? The model will be created to predict the probability of yes, because in logistic regression, the level of interest is last. But to review, if we are making predictions using month of the year is going to be a predictor, an explanatory variable. So what is going to be the reference month of the year? It would be April, because April is first, because that's a categorical X, which creates indicator variables. It's different than logistic. Logistic speaks to the Y variable, and the Y variable being categorical. So with this right here, the level of interest right here, we can still find the probability of the non-level of interest. Think about the complement we just found. So if we are predicting the probability someone purchases and we get 90%, we can get the probability somebody doesn't purchase as 10% because it's just 1 minus the probability of somebody purchasing after we take it out of the model. Now, an important thing to remember, it's not about that one person. It would be over the long run, people with those characteristics would have a probability of purchasing of 90%. This is assuming the model predicted 90%. Doesn't mean you, if you're that person, have a 90% probability. It means over repeated trials of individuals with those same characteristics, the model says in the long run, we would see a probability or frequency of 90% of the people buying with those characteristics. So how will we use this model? The important thing we will use this model for is classifying people. So when we classify people, we're going to put them into the yes group or to the no group often. Sometimes we'll have like a cat or dog group, and we'd be predicting probability of dog. Like we say, are they a cat person or a dog person? Well, dog is last, so dog's the level of interest. And so what are we going to then do with the mathematics we get from this? Well, if something has 50% or greater, they're going to be assigned to the level of interest. If something has less than 50% for their probability, they're going to be assigned to not the level of interest. So think about this. Someone has a 90% probability of purchasing, which means over the long run, people with those probabilities have 90% probability they will purchase over the long run. What does that mean? It means I think they'll purchase. I might be right, I might be wrong. So 90% right there would assign them to the yes group. 50% does assign to the yes group, and I do want to make this caveat that some algorithms inside of JUMP will sometimes flip a coin for that 50%, but oftentimes when we're doing it by hand, if it's exactly 50%, we assign it to the yes group, or you could take out a coin if you're doing it by hand and flip it and assign them to the yes or no group. But this is automatically done for us, but if we're doing it by hand, 50% or greater assigned to the yes group, less than 50% assigned to the no group, which if we're talking level of interest yes, level of interest no. Remember, level of interest is going to be the one with the higher probability, 50% or greater. We can't use the regular old regression model anymore. The regular old regression model looks like this, and if you put it on a 0-1 axis or a 0-1 y-axis, it's going to go way out of there. This is a problem right here because we are no longer bound, or we should be bound, I should say. We should be bound by 0 and 1, but this model down below is not bound by 0 and 1, which means the line is a bad idea. This is why I mentioned previously, we're going to fit what is called the sigmoidal curve, or the sigmoidal model. The sigmoidal model is bound by 0 and bound by 1, and it can't escape it. It has a limit as it approaches it. Let's take a moment and look at the mathematics here. It looks kind of complicated. The logit is what you would solve for if you solved the regression equation. So if you took your b0 plus b1x, if we're using estimates, no longer betas, we would get the logit, which is also the natural log times probability over 1 minus probability. I've really never done that equation, but I have used the logit, which we'll see down here in a moment. So the logit is the solve of the equation. Not super important, but here's what is important. The equation right here, because this equation gives us the probability. Since this equation gives us the probability, this is what you will be probably solving for on tests. When you solve for the probability right here, there's an easy way to remember it. E raised to the regression equation over 1 plus E raised to the regression equation. And what do I mean by that? Well, the regression equation is b0 plus b1x. There it is right there. So it's E raised to the regression equation over 1 plus E raised to the regression equation. It won't let me hide. There we go. That's the way I've memorized it right there. So you literally solve for the logit or the regression equation. Same thing right there. And when you solve for that, you do E raised to that. Now I want us to think about some interesting values. The most interesting value to think of here is 0. So if you have a logit of 0, we'll erase these over here, what does the probability solve out to? We'll plug it in right here. E raised to 0 over 1 plus E raised to 0 is 1 over 1 plus 1/2. And that means when the logit is 0, or the equation solves out to 0, you get the following. You get a 50% probability. We're going to do a little slash beside it, and we'll write 50%. And what's interesting is if the logit is positive, you get numbers that are greater than 50%. And if the logit is negative, you get numbers that are less than 50%. Which means as the regression equation goes towards infinity, you get values or probabilities that predict towards the level of interest. And as it goes towards negative infinity, you get values of less than 50%. This is key right here. You can solve for the logit actually if you want and know if it's the level of interest or not the level of interest. So technically, any values of 0 or higher from the regression equation solve out to something that is the level of interest. And any values that are less than 0 solve out to not the level of interest. So we will, a lot of times on the test, have you solve for this equation. So what I would suggest doing right now, if you're making your cheat sheet, put that on the cheat sheet right over there. This is what people forget to do, is we say solve for the probability from the logistic. And a lot of times when we say solve the logistic model and predict its probability, a lot of times people only solve this. But if you were to solve for that, you would then just need to plug it in to the E raised to over the 1 plus E raised to and get the probability out of it. So make sure to know how to solve in logistic regression for the probability. And a key way to know that you've solved it properly, or have a good understanding if you did, is if the probability you get is between 0 and 1. I've had people get negative values, and I've had people get values that are like 5, 8, 10, or 100. You can't get a value outside of this equation right here that is outside of 0 or 1. It must be a probability. That's because we're using the sigmoidal curve here. And notice the sigmoidal curve can be sigmoidal up or sigmoidal down. And this simply relates to the coefficient of the slope. If the slope coefficient B1 is negative, or the slope coefficient, there's the positive or negative. There we go. The negative would be sigmoidal down, and the positive would be sigmoidal up. So depending on the coefficient of the slope, the sigmoidal curve will either go upwards or downwards, increasing or decreasing the probability of the level of interest. So once again, the logistic curve may not always be the best idea. What about if we're talking baking a cake right here? So we're talking about how long we bake a cake and the probability of someone liking it. We ask them, do you like the cake, yes or no? Hence logistic regression, two-level categorical variable with a yes, no. And what you would expect right here is to see a model where there's a proper time to bake a cake. But unfortunately, in logistic, right now with our capabilities, we can only go always up or always down. Now, this is a throwback term right here. What term are we talking about where the model always goes up or always goes down, which is what the logistic curve is right now? It would be monotonic. Monotonic means it goes in one direction. And notice the logistic curve is not a good idea when we have to model something that goes in more than one direction. So this right here would be not a proper fit. We can check this later on when we check the logistic regression. Let's try to find the estimates for our coefficients in the model. Now in linear regression, it's easy. We choose the coefficients that minimize the sums of the squared error. But we don't have sums of squared error anymore because that's for a quantitative y. We're dealing with probabilities now, so we're going to do what is called the maximum likelihood principles. And in the maximum likelihood principles, you're trying to replicate your data with the coefficients you choose for your model. So imagine we have a light and we're trying to figure out the probability it's green. Only care if it's green or red in this example, and on days 1 and 4, it's green. So what should P be to replicate the data? The maximum likelihood principle is going to tell us to take the P to whatever value maximizes the chance of reproducing our data. So we could write out the equation right here, and to figure out the probability of our data is going to be this here, probability green times probability red times probability red times probability green times probability red. If you look at this, we have green, not green, not green times not green, and we get the following probability to the second squared minus, or excuse me, probability squared times 1 minus probability cubed. So now the P that is chosen will be the one that maximizes our ability to replicate the data. And you can see it here graphically where the probability of our data is maximized at a 40% probability of green right there, which is actually what we observed in the data. And this is the same way it's done for the coefficients, and it's done for us. We love that. But it's going to be so that we maximize the probability of getting our data using the coefficients that are chosen via the maximum likelihood principles. So now think about this. We have two things that need to be estimated for our model. We need to get a guess or an estimate of what the true intercept is, a guess or an estimate of what the true slope is. But these are not your traditional intercepts and slopes like you've seen before, because that's linear regression. Linear regression has a constant 1 unit increase to y, or 1 unit decrease for each unit increase in x. Not quite our interpretation, but visually what we see. In logistic regression, that difference is not constant. The curve is more steep in the center, and when you are towards the middle of the S, and kind of flattens out towards the end, where the sigmoidal curve doesn't have as much of a change when you go between 1 unit higher of x. So be careful. The interpretation here will be a little bit different. So when we interpret the coefficients, here's what we'll say. Between two individuals that differ by 1 unit of x, if it's sigmoidal positive, we'd expect the individual with the higher x to have a higher probability of y. If it's sigmoidal negative, between two individuals who differ by 1 unit of x, the individual with the higher x is expected to have a lower probability of the level of interest, y. We'll see some examples here in a second because it's not always individual, so context is going to matter. So remember, We're not saying what will happen for one person. Because imagine someone says, I want to pass the test. What can I do? We say logistic regression is not cause and effect. We would just see between two individuals where one studies more and one studies less, the individual who studies more is more likely to pass. Although I do think studying is a good thing, once again, logistic is not cause and effect. So here's where we can get our predictions. Remember what we said we could do? All we're going to do is plug in the values, like B0 right here. Plug in the value of B0 to the start of the regression equation. That's B0 right there. Here's B1 right here, which is 2. Plug that in. There's B0. There's B1. And then there is X, because that's your regression equation. This is the portion right here. Make sure to write this carefully. I'd even take this from this slide right here, because you notice it's very easy to make mistakes when doing this. exp is the function to get e, so it's e raised to the regression equation over, let's highlight that as we say it, so it's e raised to the regression equation, there's e raised to the regression equation over 1 plus e raised to the regression equation, all seen up there, and that achieves the probability. So with this right here, if we are predicting something, the probability of the level of interest here is 88%, so there's 88% probability that individuals with these characteristics would have a long-run frequency of this event occurring. Let's talk about beetles, though, and trying to use some poison to get rid of the beetles. That's always a fun topic. And with the beetles right here, we have 481 outcomes, and we make a logistic model to predict dead or live. Now, be careful, it's not dead or alive, it's dead or live. So what is the level of interest for this problem? The level of interest would be live. So if you notice right here, the coefficient of dose, which is how much poison we are giving them, is negative. So when we see a negative coefficient, we don't have to worry in logistic about the value of the coefficient. We only focus on the sign when interpreting it. Let me repeat that. In logistic regression, when interpreting the coefficients of the slope or sigmoidal curve, we only focus if it's positive or negative. So between two beetles that are otherwise identical, we're not in multiple world yet, so between two beetles, where one gets more poison and one gets less poison, the beetle with more poison is less likely to live. Now you can flip that and say more likely to die. You'd just be taking the complement right there and kind of making it sigmoidal the other direction. Let's see this visually though. Visually speaking, you can see the level of interest here on the y-axis, probability of live. So once again, between two beetles, like one that gets a 10 dose and one that gets a 12 dose, which is a 2-unit difference, the one that gets the higher dose is less likely to live. Notice how it's sigmoidal down. And we know it's sigmoidal down because the coefficient is negative, so we know the curve would go in a down direction. Once again, the curve is an S shape. Now, something I want to point out with this code, which is huge, is you no longer will use LM, you will use GLM. Additionally, you will need to add family equals binomial right there. So there's two things you need to add to the code to write a logistic regression into R. Use GLM, which is the generalized linear model, and use family equals binomial, meaning you're predicting a 2-level categorical Y. Interestingly, just as a side note, we already had a family for the previous one, and it was the Gaussian curve, which is the normal curve. So you can actually use GLM for regular linear regression, and it assumes Gaussian by default. But a lot of the codes and functions we use in this class don't mesh well with using GLM. So only use GLM at this point, at least when you're doing our assignments. For logistic, it is possible to use GLM though, the generalized linear model. For the linear models, which would be family equals Gaussian. So what about that intercept though? Well, the intercept has a really interesting quantity to it, which we'll investigate here in a moment. Here's the intercept right here, and here's the slope, and we can use this to make predictions. We'll just put it into the e raised to the regression equation over 1 plus e raised to the regression equation, and that'll give us the probability of a beetle or beetles on the long run frequency who get 20 units of the poison dose. In the long run frequency, 9.88% of them will live. About 90% will not live. And so that is the probability right there in the long run frequency of beetles that get a 20 dose of the poison. We've got people donating to a charity right here. Notice it's sigmoidal down, and we have donate no. And so what is the level of interest? The level of interest is no. because no is last alphabetically, so we're predicting probability of donate no. And notice log income has a negative coefficient. That means between two people where one has a higher log income, which is basically income, between two people who differ in their income by 1 unit, the person with a higher income is going to be less likely to donate no. That sounds weird, so maybe I would flip it. I said less likely to not donate. You can flip less to more and not to yes. So between two people who differ in their income, the person with the higher income is more likely to donate is also an acceptable interpretation. Now look at this curve though. Here's what's interesting. When you take a moment and look at the curve, you'll notice 50% is right here. So there is actually no level of log income that would achieve the yes level, which is down here. Everything above this line is no because it's above 50%. And so everyone in this model would be predicted to donate no because we never achieve a model that's high enough. Now, if you say to me, Brian, that's not the sigmoidal curve, I would say, yes, it is. It's a different curve right here, but a lot of people have said to me that's not an S-shaped curve. It's just if you zoom in really close on these S's, it won't look like an S when you're zoomed in. So we are looking at S-shaped curves. It's just that you have to go really far out sometimes to see the S shape. It's not an S shape right there. But it can look a little bit linear to people at times. It's just because they're pretty far in on the curve and they don't see the actual S shape to the curve. Here we are with another model of the donate. So it's donate no. So this is increasing the probability of donate no. And it's months since last donation. So as you would think, between two people who differ in their months of last gift, the person with a higher distance away or more months since last gift has a higher probability of not donating. And once again, we pretty much see that everybody is predicted to not donate right here. What's interesting is that this is super statistically significant, but really doesn't have us predict any differently for individuals because everyone is predicted to not donate. So there's not much going on right there with the model. Remember that the logistic curve is an S-shaped, even if you don't see it. So remember how we have positive coefficient means sigmoidal up, and negative coefficient means sigmoidal down. There's a negative coefficient on the x variable, sigmoidal down. Here's a positive coefficient on the x variable, sigmoidal up. Next, we'll get ready for some multiple logistic regression.